explain what I mean on this part just a little bit better. Here's my final marker. There may not be any. Where's Sam's markers? Oh well, I have a picture. So really we ended with, okay, here's effect size. It's the same effect sizes as ANOVA, but explaining what this proportionate reduction in error thing is. So with regression, R squared, sometimes it's called proportionate reduction in error, so it's how much we're reducing the error variance by adding the predictors. It's also called the coefficient of determination because it's got, of course things have to have 3 names. But it's this idea of like how much better are we at predicting someone's score if we use the regression line, the predictors, instead of the y-axis. So we did, the equation was y equals a plus bx, right? So we have to intercept the y, the mean of y. How much better are we getting if we add x is the question. So here's an idea, an example. Looking at grades versus the number of absences, I love the way they phrased it, and this would be the intercept, right? So the mean of y. And the distance between the dot and the lines is the error. So how far off we are from predicting their actual score. And that's a lot of error. We got, what, one person right and one person close. So what R squared measures is how much better we get by making it a line, adding this absences thing. So how much closer are we to the dots by going from just using the mean to using the slope. So the idea behind R squared, or reduction in error, sorry, back up here, is how much are we decreasing the error, the difference between y and y hat, by adding x, or x is. So it's an effect size, it's measuring how good, how useful having those predictors is. So a couple more just little issues with regression. So the standard error of the estimate and the regression of the mean, I have both of these on slides. Let me just show you. Oop, what did I do? There we go. So standard error of the estimate. We've talked about standard error all year. Everything has been mean minus mean over standard error. And B is not really any different. Right? It's a type of correlation. So it's x minus its mean, y minus its mean over standard error. And so standard error is the distance between the line and the actual data point. And since I don't have a marker, let me just back up. It's here. It's this. So how far off am I from predicting their actual score? So here's y hat, their predicted score, here's y. Their actual score, that's the error. How far off I am from predicting them.
This is so much easier to understand than like the F distribution where you'd be like, well,
it's still t. I mean, the errors are still t distributed, right? That's often called least squared error. So where this is going is the type of math. So the way that B gets calculated, since we didn't really talk about how that's calculated because it's kind of gross math, is by reducing the standard error. So it's the lowest standard error possible. It's just called least squared error. Yeah, come on. And the math is called least squares. The smallest amount of error. If I look at both of these and we ask which one's going to have a bigger R squared and it's going to be a better predictor, it's going to be the top one, because the dots are closer to the line. So just like with correlation, the closer they are to a straight line, the better the prediction. So the bottom is the same regression line, but R squared would be smaller. So we get smaller standard errors and bigger R squares, so they're inverses for the first one, larger standard errors and smaller R squares for the second one. Another big problem that we have with regression, other than the whole outliers and all the stuff we talked about for correlation, here's a new one. Got regression to the mean. Regression to the mean is when you're measuring things, especially over time, people's scores, if they're really high or really low, tend to regress towards the middle. So what you'll see this with stocks, especially stocks that start hot or start cold, they tend to regress towards sort of the average. So those extreme scores, and this picture, I don't know, it's from the book, but anyway. If I have extreme scores, they tend to regress towards an average. This is why you see some people have problems with smoking and weight loss. So even if they start high, naturally people will just come down, right? Or if they start low, people might start to come up. But then after even if they hit bottom, so to speak, for smoking, they'll still regress back towards the middle. Okay. This is not a good picture of that. Okay. Here's an example from stocks. Okay. So if we started really high, so this one started at 20, this one started really low, they basically both regressed past each other. This one, bless you, regressed towards the mean of 13, and this one regressed towards the mean of 13. So they both kind of came into this. So sometimes our regression equation has nothing to do with our predictors and has to do with that fact. But that's really hard to test. So it's just kind of something you have to be aware of. The last little bit, and then we'll do a multiple regression example, is multiple regression, stepwise, and sim. So multiple regression is where I have more than one predictor. Okay, so we're going to try that in a minute with our RP4 data. And so you basically have two hypotheses or more tests going on at once. Most people do use multiple regression. Simple regression is not really that common because if you've got lots of predictors, why not use them? Okay. Stepwise regression, and I only talk about this because it's in the book. We talk about this in my other classes like XNA, don't do this. Okay. So it's a type of multiple regression where the computer, basically the math, determines what variable is the most important and gets to be included in the regression equation. So let's say that you have like 20 different variables and you're not sure which one is the best. It will pick the best ones for you, so the strongest one mathematically. It is not the default anymore, but it is an option in many computer software programs, not the one we're using. The strength of Stepwise is that it allows us really to explore. Okay. I totally disagree with this sentence. This is from the book. This is science in me is like, oh, this is bad science. The idea behind Stepwise that to me makes it useful is if you are trying to reduce a large number of variables and you know they're all highly correlated. So we'll use things that we expect to predict, like we have a study where we're using meaning in life and PTSD and depression. Those are highly correlated. So that'll allow me to pick the best variable. But that's still based on theory. I know theory-wise that this thing is important, but I have too many of those variables. Let me pick one. So it allows us to reduce data sets. The criticism of it, and really in our field, the biggest reason people don't use it is because it doesn't rely on theory, and we're a theory-driven science. So people tend to try to use it in exploratory ways, and they say, we are exploring. But you don't see these printed very often, in psychology anyway, because people say, well, that just relies on the math for that data. And people are weird, remember? So just mathematics on one weird sample doesn't tend to appeal to people. Sim is awesome stuff. I love it. It's also a big thing I do. Okay. So structural equation modeling is regression on regression on regression. It's regression on steroids. And what it does is allows us to create these pictures of what we expect to have happen. So let me kind of show you a picture. And I'll go back to that slide. So it allows us to take variables that we've measured. Those are the squares. So anytime you see a square in one of these pictures, it's an actual variable they measured in the data. And estimate these circles. So these circles don't have real numbers. That's the hardest part. When I teach this class over the summer, they're like, but I need a number to it. I'm like, there are no numbers for this circle. It's a circle because circle of no numbers. I don't know. And what it does is it allows us to take several different variables and combine them into one. So anytime you've taken a Stanford Binet or Waze or Whisk or the 600 other IQ tests, they're estimating your IQ. But they have lots of questions they do that with. Same idea. I'm taking all these questions and I'm estimating an unknown. And so it lets me create this picture of the relationships between variables instead of just doing one regression equation at a time. It allows me to do a bunch of them at once. And so this particular one from the book is about parenting and emotional adjustment. So the idea is that positive parenting leads into a mature identity, don't ask me how to define this, which is correlated highly with emotional adjustment. So it allows us to build models, these pictures of the data, and see if that works. And this is where you really get into exploring. So you'll have different variables and you'll see if they, how they connect. So it allows us to think of this leads to this, which leads to this. And in regression, you can only do this leads to this. So if you're stuck with one piece, and Sim allows you to do a bunch of them at once. Plus, I just like Sim is a lot of fun. I don't think the building is level either. Anyway, so let's try one more regression example. And then we'll probably move that quiz to Monday. Or today's Monday. Wednesday. So I would love for you guys to pick today several variables. So let's go with clout, because that sounds like fun. As our DV, I still don't have a marker. Keep looking for one. I'll just write it up here. So let's use clout as the DV. What would we expect to predict clout?
Probably the emotional, like, if it's, well, is there a column for authority?
I think so.
Yeah. Something like authority and emotional.
Hold on, sorry. Phone, stop. Okay. Authority. I think there is.
What about power?
Power would be a good one. I know power's in there. Whoop, spelling.
Yeah.
There's power. I thought authority was in here, but maybe not. Some other ones. We need at least 2. I was hoping for 3. So we could use authentic if we wanted to. Reward, whisk, achieve. Maybe affiliation for your authority one. Let's try that. Oh, let's do tone. Tone's a good one too. We'll throw a bunch of variables in there. Right? So let me save this real quick. And yes. I'm clicking on all the wrong things this morning. There we go. So I'm gonna put this under lecture notes and then chapter 16. Just waited less time.
So how is the multiple regression not type 1 error?
That is a good question. Let me get this uploaded real quick because I have a squirrel brain and I can only do one thing at once. It's the end of the semester. In the same way that we used Bonferroni to control for type 1 error when we did multiple tests, the same thing happens when you put them all in one regression equation. You lose degrees of freedom because for every variable you add, you lose a degree of freedom. So remember we talked about it's one for x, one for y, and another one for the other x, and another one for the other x. So it takes away power to control for type 1. Does that make sense? Yeah, without getting too crazy in the math. Okay, so I got it up there. It's multiple CSV. I opened the chapter 16 thing that was already up. So I'm going to import dataset from text file and pull in that giant multiple regression one. Okay, 92 variables. What are you doing, computer? whatever, it'll be fine. It decided those columns are still there. Now, one thing we're going to have a problem with is we're not going to be able to do a plot because we don't have one x and one y. At the end, I'll show you how to do the plots. So this will be one of the options on the test. There'll be I think a couple correlations, a couple of regression questions, so that you can pick to do the essays or the multiple choice or both. So this will be one of them. Not this particular one, but a multiple regression. All right. So then we did a couple of different IVs. Let's see what we got. Power, authentic, affiliation, and tone. So, to do this, and I'll upload this at the end, we still have to come up with our assumptions. So, x, z, and y have to be scale. And in this case, they're a ratio scale because they're percentages. And we'll just leave the zeros in there this time. They have to be normal. All of them. Well, we've got way more than 30 people, so we can assume that it's normal. Like 58,000 lines. Random selection, sort of. I don't know that we really randomly selected. Nah. Random assignment. I also didn't really do that. Because they didn't get randomly assigned to be 50% cloud. Or, this much analytics. It just was what it was. So this is a correlational design. And then we talked about homoscedasticity. There we go. For that, I'm going to have to make a plot. You could plot every single x against y, but that takes way too long. So we're going to plot the fitted values against y. Okay. What does that mean? That's predicted scores plotted with y. To get those, though, I've got to run the regression equation first. Okay, so we're actually going to check that assumption at the end. And what that does is it takes all of the x variables and puts it into one score, so you don't have to check each one at a time. Right, step 2 is the same old step 2. Save this too real quick. So our research is that we have a couple of different x's here. So these variables predict clout, or that the b values are not equal to 0. Okay. Because remember, the null, or the population, is where none of this predicts. For the null, it's that they do not predict clout. I like this as BS equals 0. I didn't even think about that. The B's, plural, are equal to 0. So we're actually going to test 4 B's at once. This is actually 4 different hypothesis tests all together. If we're interested in the predictors. So step 3 is where we're going to run it and get the actual B values. So the output from our regression. So let's see here. This is an example. Or here, I want to just go down the end here and add some more. Oops, wrong thing. Oh well. There, it's a little bigger. So remember, the way we did this was we did output equals LM for linear model. I'm going to put the DV first. So clout. Spelled correctly, is approximately, so the tilde, which is above the tab key. Oop, clout's got a capital C. And then the other variables. So we're just going to add them together. Power plus, order does not matter, authentic plus affiliation, ooh, spelling, plus tone. So on the first one, all we did, it's right here actually, negative emotion was equal to positive emotion, that was just one. Now we're just adding them together. So it's going to test y equals x plus x plus x. Data equals, and then I called it multiple. Let me run that. When you run that, you will have saved the output, because we're going to need that output here in a second. So to see the output, do summary of output. And you should get this giant thing. How did they come out all significant? That's kind of cool. Probably because of lots and lots of data. Okay. Now these are all in the same scale because they're all percentages. So we can compare the B's directly, but we're also going to talk about beta here in a second. So I'm going to highlight the piece you need here is this. So we're not going to test the intercept because I'm not interested in that really. But this is what I'm interested in. Okay. It does also give me the degrees of freedom down here, which I need for the next step. Okay. But degrees of freedom, where did that come from? It deleted some people that were missing some data, and then it did -1 for each x, so 1, 2, 3, 4, and y. So it did -5. But it's easier if you just look down here where you see the second df here. It's the same one as this one. So step 3 is include the B's and beta. Beta is in quantsci. If you're on a school computer, you'll have to install that first. And remember the code for it is just lm.beta of the output. Don't do of the data set, it'll freak out. And here are my beta values. So which predictor is the most useful? Well, it looks, if I ignore the negatives, remember these are standardized values, so they're z-scores. And looking at these, power and tone are pretty equal, and they're small. Authentic is the bigger one, 0.24, and affiliation is the largest. So affiliation is probably the best predictor, then authentic, then power, then tone. So using beta, I can compare them. So we talked about how if they're not on the same scale, it's really hard to compare them. And even though these are on the same scale, that doesn't quite play out into the same numbers. Okay, they're close. But it looks like affiliation is like 3 times better than everything else. Right? When really, if I look at the standardized value, it's better than authentic, but maybe not that much better. Yeah.
It's probably because I'm not thinking of beta appropriately, but why, if like power and tones beta scores are so small, why was it a significant? Like, why did it return significance for all of the?
2 reasons. One, the sample size is just
Huge. Okay.
So power. 2, small scores can still be significant predictors. They're just small effect sizes.
Okay. So beta is effect size.
Yeah.
Yeah.
It's a z-score.
That's why I knew I was thinking.
Yeah. It's not the one people traditionally use, but it's a good proxy.
Okay.
Yeah. The thing with beta, the reason people don't necessarily use it is because it is z, so it can't get bigger than 1. So sometimes people use a partial r squared.
Okay.
So we talked about partial correlations. That's what they use instead.
Okay, that makes sense.
Anyway, okay. So if you ask me which predictor was best, hint, right? I would say affiliation. It has the largest beta. And remember ignoring the sign. The sign just tells you which direction it's going. Okay, where am I at? Oh, step 4. We did a two-tailed test, so we're going to use QT. 0.05 divided by 2 for two tails. I'm going to take this degrees of freedom here, stick it there. And lower tail equals false. Remember, that's probably going to give us 1.96 because it is so close to, it has at least 100 people. Remember, T and Z are very similar with bazillion people. So 1.96 plus and minus. So don't lose simple points because it's a two-tailed test. Remember, there's going to be 2 cutoff scores. It was plus and minus. Oops, sorry. Step 5, we got to do T found. Those are all right here. Okay. So this column is T here. First 2 are B and standard error. This one's T. So let me make those blue or something so it's clear what I'm looking at. Oh, that's not readable. Sorry. How about gray? I've made it all unhappy. These numbers. So are they all significant? Well, remember it also gives you the little stars, which is really helpful. And they're all bigger than 1.96. Some of these are ridiculous. Like 95 is just ridiculous. So they're all significant. So step 6, here I would want to talk about each variable. So power, reject, authentic, reject, affiliation, which I cannot spell to save my life. There we go. Reject. And tone. Okay, I could have said all reject, but the idea is that we're thinking about each one separately. They're all significant. What does that mean? If I look at the prediction direction, so let's look here. As power increases, the clout words also increase, which isn't too surprising, right? So as these power words are used, people have more clout. I think that's part of the equation, though, so that might not be a fair example because clout is calculated from other columns. As authentic words decrease, clout goes up, so that's kind of fun. So as people are using less authentic language, they have more clout. As affiliation increases, clout increases. And as tone increases, clout increases. Okay, so you're looking at the positive and negative part for that. The strength we did with beta. So similar idea to correlation. The sign tells you the direction, beta tells you the magnitude. All right, well, we've gotten all the way through here. But we still haven't figured out if it's homoscedastic. Probably not. Remember last time. What I'm going to do is I have my example graph from last time, so I'm going to copy that. Okay. So ggplot. Oh, right. I think I could remember that it's not installed on these computers. But what we're going to do is we're going to pull the fitted values out of here as soon as it installs. There it goes. I think. All right, yeah. So I'm going to run all this, blah, blah, blah. Okay. But when we get to the plot part, okay, I still have my data set name, so it's multiple. My aesthetic, here's where the X part is going to be. For multiple regression, this is the only one. This is blah, 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 blah. We'll do this for multiple regression only. So instead of having one X, I have multiple X's, so I need to combine those. So we're going to actually use y hat here, which is our predicted score. Okay. So it's output, $, fitted values. And that won't change. As long as you call it output, it'll still be output $sign fitted values. That is going to give me every person's predicted score, which I will then predict against their real score. So in this case, their real scores are clout, capital C. So my X is predicted score. Y here is real score. Let's see what that looks like. Oh, that looks like it did not like that. Oh, I know what the problem is. Oh, this might delete all the lines. That might be bad. Hold on. The problem is that it doesn't like... I think I can do this too. I think. Hold that thought. This is not something you have to know how to do. No. Damn it. That's just log regression. Okay, so the problem that we're running into is the fact that there were some deleted scores. So to fix that, just sort of quick and temporary, it's like this. Let me see if that works. You will not have to do that on the test. Okay, fine. It's not going to plot for me. But this is how you would make a plot, and we will not work with a stupid data set.